G'day chemistry students. In this video, we are focusing on an analytical technique called gravimetric analysis. We have completed this technique in previous modules a fair few times, essentially using mass to determine amounts of substances present and using that data to be able to complete relevant calculations. We're going to do another one of those again today. It's going to be a little bit more focused around looking at determining the composition of ions in a substance. But when we're doing that experiment, it's going to actually allow us to have a bit of discussion around this concept of yield and this concept of purity as well. Again, two concepts that we've looked at a fair amount through the module, but nothing where we've looked at it as sort of an explicit topic. So first off, going all the way back to module 2, one of the first things that we did in quantitative chemistry was learn how to measure mass. And in particular, we were weighing liquids by mass. So the technique that I showed you was always take the mass of the container, then take the mass of the container and whatever substance that you're adding so that you can take a difference. There are a lot of reasons why we might want to do this. One, if we're working in an active lab, we may not be able to tear a beaker and then come back to it teared and ready to go once we've added our liquid. That means that other people may not be able to access your equipment, and or you may lose your tearing if you walk away and then someone else comes and tears your scale, which means that you've lost all of that data forever. And in some cases, that might be data that's non-recoverable, even though you've already started your experiment. Another reason may be that you want to take a series of measurements as a reaction progresses or something like that. And to be able to account for those mass changes, it's really important to know what the mass of your container is as well. In our lesson in particular, we're going to be looking at measuring the sulfate content in lawn fertilizer. The reaction that we're going to be undertaking is a precipitation reaction specifically. So if we have barium chloride and react it with the fertilizer, which should contain ammonium sulfate as one of their active ingredients, we should be able to form barium sulfate solid as a product because it's insoluble, and then also have our ammonium and chlorine ions present still in solution. Once we've made the precipitate, what we should be able to do is filter it off from everything else, measure the amount of barium sulfate that we've got by mass. That's where our gravimetric analysis concept comes into the experiment. And if we know the mass of barium sulfate that's present, we can calculate the amount of sulfate ions that were present and sort of work our way backwards mathematically to figure out what the composition of sulfate was in the original fertilizer that we used. If you want to read a little bit more about the steps that we're using, are pretty much an adapted version of this practical at the website below about lawn food. You're more than welcome to have a read before we get into the lab. Something that we will be focusing on though is yield. So when exploring the concept of yield, we're generally talking about how much product was produced based on available reactants. So we're talking about the portion of product that was produced based on how much could have been produced from the amount of reactants that were there to begin with. So essentially, we are often asking the question, how much product did I produce compared to the theoretical maximum amount? This brings in things like limiting reagent concepts into play that can be used to figure out how much of a theoretical maximum we could make. When calculating yield, we generally look at that as a percentage. So, I made 90% of what I possibly could have made in theory. I made 50% of what could have possibly been made in theory, etc. So that's a percentage value. And we take the actual mass that we made, divided by the theoretical mass that could have been made based on the reagents that we had available to us and the amounts, and multiply that number by 100. It's a simple percentage calculation. So when looking at yield, there are some factors that may increase the amount of product that we make, but there may also be some factors which reduce the amount of product that's made and making it less than the theoretical maximum. So some things that we could consider to try and increase yield, maybe if we had an equilibrium, try and shift it towards a product side. And that could be done through concentration changes, temperature changes, and volume pressure changes. We could also try and recover some of the unused reactants that were there in a process and recycle them again. That could increase the total yield that we have. Another way of increasing yield could ensure that we give the reaction ample time to complete. If we stop the reaction before it's actually done, we may be limiting the amount of product that's made. That can also be enhanced by the use of catalysts. While catalysts won't increase the yield, it will reduce the amount of time that you would need for the reaction to get to completion. Generally speaking, we need to keep into consideration ways where we may lose mass during the process. This may help to explain why we don't actually attain the maximum yield that we were looking for, or that was theoretically possible. And generally speaking, when trying to explain why yields are hitting that theoretical maximum, it generally comes down to the design of the process itself. Another thing to consider is purity. When we're looking at purity, we're reflecting on the product itself and whether or not we actually made the desired compound or how much of the product was actually the desired compound. So really what we're thinking about is, are there any impurities? Are there things in the product that shouldn't be there? Very similar to percentage yield, we can calculate percentage purity as a way of measuring or discussing how pure a substance is. We look at the mass of the substance that is the desired compound and divide it by the total mass of the product and multiply that by 100. So reflecting on purity and thinking why it's important, when we're looking at synthesizing chemicals, we can use them for a lot of different purposes. And that may require a certain standard of purity. Certainly could require that certain contaminants should not be a contaminant at all. So the required purity will be dictated by their purpose and the reason for being used. And in particular, safety considerations need to be considered as well, because some of those contaminants could be harmful or dangerous. When we're thinking about all those things, we should be reflecting on whether or not they're used for, say, rinsing, cleaning, or being a solvent. If those things aren't for human consumption, then generally some contaminants are a little bit more excusable. When looking at, say, a reagent for synthesis, contaminants could be a really big problem because that may lead to the production of undesired products in that actual synthesis reaction, and those contaminants may not be desired. For analytical use, very similar. If those contaminants are present, then we may not be able to analyze with the precision and accuracy which we require. In the pharmaceuticals industry or for human consumption, really important to not have contaminants that are going to be dangerous to people. They're the people consuming them. But for something, say, like production of fertilizers, we may not need to be so strict with the contaminants that are present. Obviously, we want a high degree of purity to be able to provide high quality fertilizer to gardeners and farmers. But if there are contaminants that are present, it's probably not as important to remove those contaminants as it would be if those materials are being used for human consumption. So when we're looking at purity and why there may be some differences in purity, generally we're looking at contamination itself. Did you bring anything into the substance that shouldn't have been there to begin with? Contamination could be happening in externally or internally. So some ways that you may have internal contamination is that you've ended up producing something that you didn't exactly plan to produce. And that may come down to the quality or the purity of the reagents that you started with, but it could also be because there were some chemical reactions that were undertaken that were not desired or weren't planned in the design. You may also have some contamination because there were some substances that were not separated from the desired product. And all of these elements that I'm discussing essentially can all be boiled down to the design and the execution of the process used to actually make the chemical itself. Thank you very much, everyone. So yeah, we'll look at some of those concepts when trying to determine the sulfate content of a lawn fertilizer. In the next video, what we'll look at is another analytical technique for trying to measure the concentration or amounts of a substance in a sample by doing something called a precipitation titration. But until then, have a good one.